Okay, welcome back everybody. I want to continue our lecture, and this will be the last for this series regarding chaotic processes for the class. This is lecture 11 for the class Chaos and Fractal Dynamic Systems. We have been going through quite a bit. We've gone through a lot, and I will commend you for sticking with me so far. And here are the things that we've talked about in relation to the Colpitts oscillator as our foundation. Now I'm going to actually introduce, or at least utilize, I should say, the Lorenz system for the two discussion items that I want to carry out today. But we've used the Colpitts oscillator as a foundation for the background, the characteristics. We talked about the butterfly effect. We introduced Poincare surfaces. Synchronization we talked about. Controlling chaos we've talked about a little bit. We've talked about symbolic dynamics. We just want to continue to have this discussion as I kind of introduce some notions about image processing and encryption. Now, so what we've said, and as you can see here, is a pretty well populated attractor for the Colpitts oscillator. And what we've said about this attractor, this is where the motion of the system lives. It's drawn to this space that we call a state space. And in this case, the states are that of the current that flows through the inductor in the circuit, the voltage across the emitter, and the voltage across the collector. And that is enough information to determine the state of the system at any given time. And if you track that over time, you generate a state space, which is what you see here. And in this case, it is a chaotic attractor. The Poincare surface that you see here is erected to begin to get some more information about the dynamics of this system. So, as you look at this, and this particular surface that is erected here, I'm kind of overdrawing it, right? It cuts through, and there's an arc that is generated through here. And it's better shown on this next slide. This is the arc that cuts through the Poincare surface. And as you see on the picture, the surface is erected at a constant current value, somewhere on the order of 0.015 or something like that, right? And so that slice then would show the emitter voltage and the collector voltage, and these are the points that it's passing through. Now it doesn't pass through in order. It'll jump anywhere on these, this surface back here. It can jump back here, back there, then down here, and so on, and begin to just fill up this arc that runs through the Poincare surface. Now, we went further to say that if you then look at the return map for either the collector voltage or the emitter voltage, and that means if I track a point on this Poincare surface, let me go back to it. If I track a point here, where does it show up next? And it could be all the way over here. And then the next point might be here. Well, there's a mapping that allows you to see its actual dynamics, and that's what this return map is. And if you can remember, we did this for the logistic map, which was a single hump map. This kind of has two of them, but if you draw this line that goes through from, this is the x equals y line here, or I'll just say VC equals VCN plus 1. Let me write that better. That looks awful. This is the VC of n equals VC of n plus 1. Or, x equals y, right? That line, because this is 9.6 to 11.2, this is 9.6 to 11.2, so the straight line through there. Now, why do I do that? Because if I came in, say I came in at 10, okay? So come into the map at 10, here's 10. For V sub n, you project over to the, onto the x equals y line, and then when you hit that line, you project downward, and this is where you get your next point, right there. And if you want the next point, you do it again, and you project over. Oh, I messed up. Oh, no. Draw that line again. Project over to the map and down, and there's the next point right there. So let's just say this was point 1, and this is point 2, and this is point 3, and now you project over again to the line and up, and there's the next point, which we'll say that's 4. And you can keep doing that, and this shows you how these points are generated. And you can do the same thing here for the emitter. So that's how the map is formed, but you can also go a step further to generate this symbolic dynamics, and that is to say you create this generating partition and you can assign a 0 here and a 1 for everything that falls on either side. Now, so let's do this same mapping procedure. And say we start here. All right, so that's on the 0 side, so we generated a 0. Then we project it off of the x equals y line down to here, and now we've generated a 1. Do the same thing again, over to the line, project up. Now we've generated a 0. And do the same thing again, project to the line. It's down here, so we've generated a 1. So what is the sequence? 0, 1, 0, 1, and if you keep doing it, as you can see here, it's going to generate a 0. All right, so 0 and so on. So this thing is, if you let it run, it's going to generate a bit sequence. Okay? Now I showed that a little further on here. We talked about everything I just said. And even on the map itself, you can see that where this partition lives is about right there. So again, everything that falls over here is a 0, and everything that falls up here is a 1. And still you can track what's going on. So what would actually tell you then is that the sequences, and I'm not going to try to project what they are, but all the sequences that are launched from here are going to start with a 1. So let's say that's 1, 0, 0, 1, 1, 0, 0, 1. This sequence here, whatever that might be, let's say it's going to start with a 1. It might be 1, 1, 0, 1, 1, 0, and so on. All the ones that fall over here are going to start with a 0. So that might be 0, 0, 0, 1, 0, 1, 1, so on. This one might be 0, 1, 1, 1, 0, 1, so on, right? You could eventually, if you ran it long enough and the system itself was robust enough, you eventually would generate all the sequences. Now, as we also mentioned, now say for instance we wanted just a 8-bit sequence. There are 256 different bit sequences that are 8 bits, right? That's 2 to the 8th equals 256. Using a simple example, let's just go, 2 to the 3rd is equal to 8. That means there's 8 different sequences if we just of 3 bits. And so you'll see that you have, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, which is 1, 2, 3, 4, 5, 6, 7, 8 different bit sequences that are 3 bits long. Where if you go 8, you have 256, 2 to the 10 is 1024, so on and so forth. So you could generate a limited number of bit sequences, and if you can do that, just say we did it with just 8. Well, if you could generate all 256, well, you can string them together and make any sequence you want. Now that you can do that, and for all time. So having a limited set is not a bad thing. It just, constricts how you can do it. So that leads me to this. So how could we, say, encode an image into a chaotic system? All right? Well, first, you need to figure out how to actually look at an image and determine how is it encoded into a binary sequence. Well, most of you know Star Trek's my favorite thing of all time. And so this is a picture of the Starship Enterprise. It's 100 by 100 pixels wide. And each pixel, this is a 24-bit color image. Now, 24 bits give you millions and millions of possibilities, right? Because 2 to the 24th is a big number, 1 million something or other. All right? So how are they arranged? Well, each pixel is represented by 8 bits. So you have 3 sequences for RGB. That's why you hear about RGB color. Each one of these has 8 bits. That's why you get 24 bits. Now, what these are the intensity levels for each of the colors. So the intensity level between 0 and 255, is low, 255 to 255 is 255 to 255. 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 to high intensity. So a white image, all white on your picture would be 255 in all of these because it's the brightest. And you know, black would be all zeros everywhere. And of course, an image is is all of those things connected together. Now, so pulling exactly from this image at the position 40 in X, so let's say 40 is about right there, 50 is in the middle, so somewhere right in here, the value of 84, 98, and 101. And as you can see, that's a gray color, right? Which tells you that, yeah, they're probably very close to all being the same intensity, but maybe a little bit more blue, right? So you see blue is a little bit higher than the others, but they're all about the same. Which would give you a grayish kind of thing. If it was all at 255, then of course that would be white, and if there were zero, there'd be black, but so somewhere in the middle, which is gray. So this kind of jibes with our understanding, right? So the whole 24-bit word would look like this. And this tells you now the size of the image itself is 100 by 100, 24 bits. So there's 240,000 bits. And in order to turn it into bytes, you divide that by 1,024. Actually, I should also divide it by 8 because there's 8 bits per byte. So actually this number needs to be divided by 8 in order to be accurate. Okay, so, and if you want, let me just do that. I'll just say 234. 234 divided by 8. So this is 29. This is really about 29 kilobytes. That image. And that's uncompressed. Now, I read this in as a JPEG into MATLAB, and it itself was much smaller. So that's after being compressed. Now, I won't talk about compression. It's a little too much for now. But this is how an image is arranged. And these are the sequences. So as you move through the whole image, you go 100 by 100. So there's 10,000 points. Each 10,000 have these sequences. You string it all together. That's just a run of 240,000 bits. And that's essentially how things get sent around on your wires, wirelessly. They're sending a signal that represents bits. So now let's try to see how we could introduce a chaotic oscillator into this. Keep in mind that these sequences are just strings of ones and zeros, and any digital piece of information, whether it's an image, whether it's a video, whether it's sound, whether it's a text document, whether it's a file, whether it's a code, whether it's an app, they're all just collections of ones and zeros. And if you can send them around, you can send everything. And that once we started making that transition, I was, in the midst of technology, doing all this stuff around the 80s, when everything was going to digital. Now, anything that we generate, anything that we do can be represented in a digital format, and therefore can be sent over any type of medium. And that's why we enjoy all this stuff that we have today. So I want to now, let's take a look at the Lorenz system. Why because as you can see, it kind of naturally lends itself to two separate spaces for ones and zeros. So if I decided that over here, anything that kind of hits over here is a 0 and here's a 1, that's a natural thing. So I'll go ahead and tell you that a good place that we've put a Poincare surface is two of them. One right here, kind of starting in the center there, and another one over here. So you can create this mapping again from that. And this is just the different versions. Here's the different views. This is the three-dimensional view, and here's the two-dimensional projections looking from each axis, X and Y right here. Here's X and Z, and here's Y and Z. So from either projection, there's naturally a place that tells you that you could separate this into these two lobes. So if I apply this Poincare surface, you get this. And you can kind of see that you have over here, we can assign ones, and over here, we assign zeros. And this is just for 112 points that is pierced through. So I didn't run it for very long. I just wanted to show you what that looked like. Now, let's take a look at just naturally what this is generating. Because if I looked at the peaks of all of these, I can write a sequence. Look at this. I can say 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, so on, right? So I think I stopped right about here. So you can see that this system can be a natural generator of binary sequences, and you have this bipolar signal, right? Is equally kind of centered about 0. So this is positive, negative. So with typical regular binary waveforms, digital waveforms that get sent on your Ethernet cables or wires, whatever, they typically look like this. It would look like this for the same sequence up there, right? Here, 0, 1, 0, 1, so on, right? This is what gets sent, and these are usually, 5 volts plus 5 volts minus 5 volts. But they don't end up being looking perfect, because once you send it through some sort of channel where there's a wire over the air, they get distorted a little bit, so they don't look perfectly square. So a signal like this Lorenz, that's again comes from a set of mathematical equations. You could also build a circuit that would do this. It's a nice way to generate these binary waveforms. And now remember, we said that we could control it to give us the bit sequence we want. And if we're able to do that, then we could indeed encode this image with these sequences into this particular oscillator. So what does that mean? So by controlling symbolic dynamics in a chaotic system, you can embed any bit sequence that you like. This could be an entire image, audio file, video, you name it. So let me ask you this. Since there are naturally occurring chaotic processes all around us, whether it's the weather systems, whether it's just moving clouds, water, just naturally oscillating things that tend to be chaotic, and you can look some of those up. There can be digital information embedded in them. And some of that digital information might be meaningful. So I'm just want you to think about, what does that mean? If, again, you find a natural system that is generating chaotic processes, you apply the Poincare surface or something and identify a bit sequence, and what if that digital sequence actually has a message in it? Just want you to think about that, that's all. Okay, so I want to move along to another idea, and I'm going to use this, I'm going to use MATLAB to demonstrate it, and then we'll call it a day. Okay, so we've shown that you can use a chaotic oscillator as a natural binary source. Generates ones and zeros, and different types of sequences that you can use. So suppose that we could associate unique sequences to initial conditions. So as I want to go back to, well, let's look at this one. Now remember, I said that each one of these points could source its own sequence. Remember, all the ones over here would start with 0. So suppose this source 0, 1, 1, 0, 1, 1, 0, and so on. And remember now that this is associated with a point in space. You know, X, Y, and Z. That sources a unique sequence. And so does all of these. So what I'm saying, that there are initial conditions that could generate and be associated with any particular bit sequence. All right. And then suppose that we can associate a pass key to a set of initial conditions. So let's just say, for instance, I generate a password. You know, whatever, just X, J, 0, 5, K, P. All right, I just made that up. And we could then take that, and there are ways we could turn this into a bit sequence, and that bit sequence into initial condition, and then that generates, using the chaotic map, that initial condition generates a long bit sequence. Now this sequence we would call M, we could use as a mask. So let me try to, you know, draw this out. All right, so we start with a pass key. And we take that and generate then a set of initial conditions. Okay? Then those initial conditions are then put into our chaotic oscillator that remember is generating a set of an output of, let's just say X, Y, and Z, and this then generates a bit sequence. No, I'm not going to use B, I'm going to use M. A bit sequence that we're calling a mask. Okay, so we use that to generate our mask. So a unique key code generates a unique initial conditions in the state space That runs through the chaotic oscillator, generates these points that we can use with the Poincare surfaces in here. And then we associate it to a 1 or 0, and now we've generated this mask, which is a unique bit sequence. Now, you have your file. And let's just say that that file is whatever. In the case I'm going to show you, it's an image. This image is, again, a bit sequence that is a bunch of 1s and 0s. Now, we want the length of B to be equal to the length of M, or vice versa. Let me put it that way. Let me say the length of M to be the length of B, because that's the file, you know, you can't, that's what you want. You want to match that length. So now you've got two things. Now the nice thing that we can do now is we're going to use a exclusive OR. Now, what that does is basically say you have 2 bits input, you get an output. So exclusive OR symbolically looks like that. You put 2 things in, you get something out. But there's a table that is, I'll just go ahead and use it, say, B, M, and then let's call it, just call it A. It's an output. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. So an exclusive OR will give you 0 for this, 1 for that, 1 for that, 0 for that. Exclusive OR means it's only OR, this or that, but not both. That's the only difference. So let's just use a quick example that, say my bit sequence was 1, 0, 1, 1, 0, 0. Let's just use that. And the mask is, let's say 0, 0, 1, 0, 1, 1. Okay? Then the output will be a sequence. Let's see, I guess we called it A. I'll use capital A since we. So remember, 1 and 1, a 1 and 0 gives you a 1. 0, 0 gives you a 0. 1, 1 gives you a 0. But 1 and 0 gives you a 1. 0, 1 gives you a 1. That gives you a 1. So that's what you would have as your output. So now this becomes your new file that you save. So you save that, and that's all you save. So now this is my encrypted file. You do that for 1,000,000 bits. That's your encrypted file. So then, if I want to decrypt it, we do the exclusive OR again with it and the mask. But where do we get the mask again? Well, the mask is generated from the key code. So if you have the key, that's the only way you can generate the right mask. So if you have the key, you generate the right mask. Now you operate the same thing. So watch this. I'm going to, let me get rid of that. I'm going to operate this mask on this and watch what happens. So 0, 1 is 1, that's 0, that's 1, that's 1, that's 0, and that's 0. And lo and behold, that is B. So using an exclusive OR on a mask that's generated by a chaotic oscillation will allow you to encode or to encrypt and then to decrypt. And I'm going to try to show that example. All right, so I use this picture here. I think you can see it if I double click it. Well, you can see it down here. I don't know if you can see it. This is a little picture of me back when I was a little boy almost. All right, so let me get rid of this, and so this code's CEN, and I'll just show it right here. I'm not going to give it to you, but I'll show it to you, and it's not really that sophisticated. So look at what we have here. So the initial conditions, the file name, and the output name, I'm going to add a .cn to the file. Then I read it in, and then I put in a pass key. Now this is, where I generate a initial condition from the pass key. I got a function that does that right here. This will generate the pass key from the initial conditions from the pass key. All right, and then so going back. This is just establishing the Poincare surfaces, so I know my 1s and 0s. So here's where I start running it. I integrate the Lorenz system, and I run it through the Poincare surface, and I check to see if it goes through the 0 surface or the 1 surface. And I generate this mask, which is the bit. It's either a 1 or a 0. So at the end of it, I have this long sequence of bits that is as long as the input file. Now I apply the mask. I use the exclusive OR and check each bit. And if each bit, whatever it is, I generate the 1 or 0. And now I have my new file, which I called A, but it's now the new file. And then I save it. And I save that out as a binary file. Okay? Now, in order to decrypt, I have the same thing. Read the file in, but this time I'm reading in the encrypted file. I give it a tag to show it's decrypted. I put in the key, and here's the right key code. It's the same as this one, right? That one. But this is the one I tried to make sure to show you that it won't work if I put the wrong key in. Same thing, I generate the bit sequence from the key code, which generates the initial condition. Then I make a mask. I apply that mask to the encrypted file, get back the new one, and run it. Now, instead of trying to run it, because it takes a few minutes and it'll eat up the time I have, here's an example of the file itself. Then I created an encrypted file, which it doesn't know what to do with. So the decrypted file here comes out to be the same thing. But when I try to decrypt it using the incorrect code, it doesn't work. And you can only decrypt it if you have the right code. Okay? Now, that was just an example to show you, if I had more time, I'd run it, but that doesn't do anything but just show you that it actually works. But you can do this and have your own unique code. Now, you could use any chaotic oscillator. It doesn't have to be the Lorenz, like I said, just kind of makes itself nice for binary encryption. And you could do all kinds of things like that. So this is being used. There's a lot of literature out there. I encourage you to search out some papers and take a look at it. But it's a lot of this and more. And I wanted to just introduce you to some of this, let you do your own investigation, and then just show you some neat things that are happening. Now, so as we wrap up here, I just wanted to make sure we understood everything we've done. Kind of go back to my list again. We've understood the background of chaos and it's where it's emerged from, the study that has happened over the years, the fact that it is sensitive to initial conditions, it's sensitive to small changes. You could synchronize chaos. You can control chaos. You can even encode it in such a way to produce binary digital information. You could even do more than binary if you like. You could break it up and do whatever you want to. But binary is what we use as digital. And the reason for that is just that positive and negative voltages are easy to distinguish. And switches are on and off. And that's why we've kind of settled onto this binary system, because they're easy to distinguish. So anyway, there you have it. So if you have questions, comments, things like that, feel free to share them with me. But I've enjoyed this. I hope you have too. And I look forward to talking with you more about some of these ideas.